Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the hybridization concept. So before discussing the hybridization concept, let us discuss what are the necessary things that leads to the proposal of the hybridization concept. So let's begin the class. If we take methane molecule, if we discuss the formation of the methane molecule using the valence bond theory, here the central atom is carbon, atomic number of carbon is 6 electronic configuration 1s2, 2s2, 2p2. So here valence shell is having the 4 electrons. Out of that, 2 electrons are in the s orbital and 2 electrons in the p orbital. So valence bond theory says that for the formation of a covalent bond, atomic orbital must have one unpaired electron. So with the help of these two unpaired electrons, carbon is able to form only 2 bonds. But here carbon has the 4 bonds with 4 hydrogen atoms. That means carbon requires 4 unpaired electrons. So for this purpose, one of the s electron jumps into the p orbital, providing the 1 unpaired electron in s orbital and 3 unpaired electrons in the p orbital. Altogether 4 unpaired electrons are present. And the energy required for this excitation of the electron from the lower energy orbital to the higher energy orbital will come from the bond formation, carbon-hydrogens bonds whenever they are formed. So that energy released will be useful here. So your question maybe here is, after excitation only the bond formation is taken place, then before only how the energy is coming. It is simple thing that first 2 carbon-hydrogen bonds will be formed. From there the energy will be released. That energy is utilized by the carbon to excite these electrons from the lower energy orbitals to the higher energy orbitals. Since electrons are moving from the lower energy orbitals to the higher energy orbital, this process is called the excitation process. And this electronic configuration is called the first excited state electronic configuration, and this one is called the ground state electronic configuration. So after the formation of the 4 unpaired electrons in its first excited state, now carbon is able to develop the 4 bonds with 4 hydrogen atoms. And the interesting thing in this category is, out of these 4 carbon-hydrogen single bonds, 3 carbon-hydrogen single bonds are coming from the p orbital overlap with the s orbital of the hydrogen atoms, and 1 carbon-hydrogen bond is coming from the s orbital of the carbon when overlap with the s orbital of the hydrogen. That means here, whenever carbon overlaps with the hydrogen 1s orbital, so the molecule should look like this. The reason here is, these are all px orbital, py orbital and pz orbital. Px, py, pz orbitals are oriented perpendicular to each other. So whenever they overlap with the s orbital of the hydrogen, the bond angle should be 90 degrees. So here 2 type of the bonds and 2 type of the bond angles are present. One type of bond angle is 90 degrees that arises from the p orbital overlap with the s orbital, and another one is from the carbon s orbital with the hydrogen one s orbital. This should look like a linear. And next one is, all the 4 carbon hydrogen bonds are not similar. 3 carbon hydrogen bonds are of one category because this is arised from the p orbital of the carbon with the s orbital of the hydrogen overlap. And the next bond, the last bond, is from the s orbital of the carbon when overlap with the s orbital of the hydrogen. That means a single molecule is having the 2 different type of the bond angles and 2 different type of the bond lengths and bond energies. But in reality, the shape of the CH4 molecule is not like this. At the same time, the bond angles also, only one type of bond angles and bond energies are present. So to explain this type of the concept, Pauling proposed an hypothetical concept of hybridization. So hybridization says that before formation of the bonds, the atomic orbitals of the same atom, they completely intermixes. So here this s orbital and these p orbitals completely mix with each other and produce the new orbitals. So the intermixing of the atomic orbitals of the same atom having almost equal energies and produce the new orbitals with equivalent energy called as the hybridization, and the newly formed orbitals are called as the hybrid orbitals. And what is the difference between the hybridization and overlap? Overlap is nothing but the partial merging of the atomic orbitals of one atom with the atomic orbitals of the another atom. But in case of this one, hybridization atomic orbitals of only same atom participates. So hybridization means atomic orbitals of one atom intermixes with themselves, but atomic orbitals of one atom never intermix with the atomic orbitals of the another atom. So that partial process is called the overlapping. But if only single atom atomic orbitals mixes with each other producing the new orbitals, that is called the hybridization. So we shall write down the definition here. The intermixing of atomic orbitals having similar energy of an atom to produce new orbitals having equivalent energy is called hybridization. And the orbitals thus produced called as the hybrid orbitals. Then what is the difference between the hybrid orbitals and atomic orbitals? If you take the atomic orbitals of the p atomic orbitals of the carbon, they're all having the similar in size and similar in energy. But hybrid orbitals never look like that. They have one larger lobe and a smaller lobe. Example I'll take here. So this is a hybrid orbital. Hybrid orbital is having the two different lobes, means two lobes with different sizes. The larger lobe is always signed with a plus and the smaller lobe is represented by the minus sign. So larger lobe always participate in the formation of the bond and the smaller lobe don't participate in the formation of the bond. Now here the question is, what happens, how many number of atomic hybrid orbitals are produced based on the atomic orbitals? Very simple thing, that the number of hybrid orbitals produced equals to number of atomic orbitals intermixed. That means if two atomic orbitals participate in the intermixing process, we get the two hybrid orbitals. If three atomic orbitals participate in the intermixing, three hybrid orbitals will be produced. Four atomic orbitals gives four hybrid orbitals. Example, look this side. S orbital and p orbital intermixes with each other. They produce two sp hybrid orbitals. If s orbital and two p orbitals intermixes, they produce three sp2 hybrid orbitals. If s orbital and three p orbitals intermixes, they produce four sp3 hybrid orbitals. So hybrid orbitals are represented by sp, sp2, sp3, sp3 depending on the type of the atomic orbitals participating in the intermixing process. And here we said that the atomic orbitals having the similar in energy. That means if atomic orbitals are having the different in energies, they don't intermix with each other. They must have the almost near equal energy. Example, we shall take here. So I'll write down the point here. Atomic orbitals must have similar energy, or at least near energy. Example, 2s orbital can intermix with the 2p orbital, but 2s orbital do not intermix with the 3p orbital, because 2s 2p orbitals are having the almost, they belong to the same orbit and having the almost similar energy, but 2s and 3p orbitals are having the difference in energies, larger difference is there. That's why 2s orbital don't intermix with the 3p orbital, but 2s orbital intermix with the 2p orbital. For example, here we have taken that s orbital and p orbital. So in this case, if you take 2s orbital, it could be 2p orbital. If you take 3s orbital, it could be 3p orbital. If you take 4s orbital, it could be 4p orbital. That means s and p orbitals which are having the similar energies, they get intermixed. Then only they will produce the new orbitals which are called the hybrid orbitals. And next, promotion of electron. Promotion of electron is not compulsory. Is not compulsory condition prior to the hybridization. That means here you see that electron is promoted from the lower energy orbital to the higher energy orbital before the formation of the 4 single bonds in the CH4 molecule. So that is not compulsory condition in the hybridization. The hybridization only involves either unpaired electrons, orbitals having the unpaired electrons, and sometimes orbitals having the filled electrons also. That means compulsory condition is not promotion of the electrons from the lower energy orbital to the higher energy orbital. And once these hybrid orbitals are produced, they arrange, hybrid orbitals are arranged. They arrange in space in such a way that the repulsions among the hybrid orbitals is less. So once hybrid orbitals are produced, they arrange in the space around the central atom only to reduce the repulsions between the hybrid orbitals. That gives more stability to the molecule. And the next point is hybrid orbitals always form sigma bonds. And never form pi bonds. Then if multiple bonds are present, in the multiple bonds, the sigma bond always comes from the hybrid orbitals and the pi bond is coming from the unhybrid orbitals or pure atomic orbitals. So now let us see some of the molecules and how they are participating in the hybridization process. Let us discuss the SP hybridization. So the SP hybridization meaning is one s orbital intermixes with one p orbital to produce two sp hybrid orbitals. That means you take this one s orbital, this is s orbital, and any p orbital So 1 p orbital. So to produce 2 sp hybrid orbitals. This is the positive and its respect to negative lobe. This is the positive and its respect to negative lobe. This is one sp hybrid orbital and this is one sp hybrid orbital. 2 sp hybrid orbitals are produced. So the angle between the hybrid orbitals is nothing but the bond angle. Here angle is 180 degrees and the shape of the molecule also depends on the arrangement of the hybrid orbitals. So it arranged in the linear manner. So the shape of the molecule is linear. Hence this sp hybridization is also called the diagonal hybridization. Let us take an example here. BeCl2 molecule, beryllium chloride. In BeCl2 molecule, the center atom beryllium atomic number 4, electronic configuration 1s2, 2s2, 2p0. So here valence electrons, two pair electrons are there, a pair of electrons, and 2p orbital is having the 0 electrons. But for the bond formation, unpaired electrons are compulsory, but here pair of electrons are there. That's why in this case, electrons undergo promotion. That means they go to the next higher energy state and giving the 2 unpaired electrons. Now, this s orbital of the beryllium intermixes with its p orbital and produces 2 sp hybrid orbitals. So in this sp hybrid orbitals, these two are sp hybrid orbitals of the beryllium. Once sp hybrid orbitals are created, the unpaired electrons or whatever the electrons are present in these intermixed orbitals will be distributed into those orbitals according to the above principle, Hund's principle and Pauli's exclusion principle. And in this case is above principle concept is not applicable in filling of the hybrid orbitals because above principle says that lower energy orbitals must be filled first, then go to the higher energy orbitals. But in the case of the hybrid orbitals, they are all having the equivalent in energy. That's why above principle is not applicable. Only Hund's principle and Pauli's exclusion principle is applicable. So that each of these sp hybrid orbitals occupied by the 1 electron. So this is the beryllium atom sp hybrid orbitals. Afterwards, chlorine atom is there. So chlorine atom atomic number 17, electronic configuration neon 3s2, 3p5. So s orbital pair of electrons are present. P orbital totally 5 electrons. Out of that 1 is the unpaired electron. So the unpaired electron of the chlorine that present in the p orbital now overlaps with the sp hybrid orbital of the beryllium to give the one beryllium chlorine bond. This is the chlorine atom p orbital. Similarly, this side also sp hybrid orbital of the beryllium overlaps with the p orbital of the chlorine to form the one more sp p chlorine bond. So here beryllium is having the 2 bonds with the chlorine in the linear manner with a bond angle 180 degrees. So here 2 sigma bonds are present. These sigma bonds are arised by the overlapping of sp orbital with p orbital of the chlorine. Hence we can call these bonds as sigma sp-p bonds. Now let us take one more molecule. C2H2, or simply we can call this one as ethyne molecule or acetylene molecule. So in C2H2, carbon atom is the central atom. 2 parts are present. So carbon atomic number 6, electronic configuration 1s2, 2s2, 2p2, s orbital 2 electrons are present, p orbital also 2 unpaired electrons are present. Remember that Carbon always forms its molecules only in the first excited state but not in the ground state, because in first excited state only carbon will have the 4 unpaired electrons. So one of these s electron jumps into the p orbital and providing the totally 4 unpaired electrons. So out of these 4 unpaired electrons, only one s orbital intermixes with the one p orbital to give the sp hybrid orbitals. So the concept here is, you may get the doubt that why all the orbitals are not participating in the hybridization process. Basically, hybridization is a hypothetical concept. So we propose the number of hybrid orbitals that required only for the formation of the sigma bonds, not for the pi bonds. So the remaining unpaired electrons, remaining unhybrid orbitals, participate in the pi bond formation but not in the sigma bond formation. So let us take here carbon, sp hybridization. So these are the sp hybrid orbitals of one carbon, sp orbital and sp orbital. So will be filled with a single electron, and later these are remaining p orbitals. Imagine this is one p orbital, that is unhybridized p orbital having one electron, and this is one more p orbital, one more unhybridized p orbital with unpaired electron. See, these two p orbitals are not side by side, they are arranged perpendicular to each other. Why? Because px, py, pz axes are perpendicular to each other. If you imagine sp hybrid orbitals are arranged like this in the linear manner, one p orbital is like this and one p orbital is like this. So they are not side by side, they are actually having the 90 degrees angle. Similarly, another carbon atom also participates in the same type of hybridization, so that the sp orbital of the another carbon atom overlaps with the sp orbital of the earlier carbon atom. These are sp orbitals, giving one carbon-carbon single bond. So initially we get the carbon-carbon single bond or sigma bond. And remaining, that carbon also will have the orbitals like this. This is one p orbital having the unpaired electron with opposite spin. Imagine, let us take this is px orbital, this is py orbital. So I am taking this is the px orbital and this one is the py orbital with unpaired electron opposite spin. So px orbital present on the same side. So when they overlap above and below the internuclear axis, so they produce one one pi bond. And this py orbital when intermixes with each other, they produce one more pi bond. So these two pi bonds are coming from the overlapping of unhybrid p orbitals or pure p orbitals. And the middle one is always sigma bond, remaining two are the pi bonds. And this sp hybrid orbital overlaps with the 1s orbital of the hydrogen to provide one carbon-hydrogen sigma bond, and this sp hybrid orbital after overlapping with the 1s orbital of the hydrogen produces one more carbon-hydrogen sigma bond. So here the bond angle is 180 degrees. Carbon-carbon bond length is 120 picometers. Carbon-hydrogen bond length is 106 picometers. Hydrogen carbon bond angle is 180 degrees. Shape is linear. So this is the sp hybridization. And if you would like to calculate the percentage of the s orbital character in the hybrid orbitals, very simple thing, that percentage of the orbital is equals to 100 divided by number of hybrid orbitals. Example, in this case, percentage of every orbital is 100 divided by sp hybrid orbitals means only two orbitals are present. Two sp hybrid orbitals are present. So divide by 2 so that we get the 50%. That means every orbital is having how much contribution in the formation of the sp hybrid orbitals? 50% each. That means percentage of the s orbital is 50 as well as percentage of the p orbital is also 50%. So, dear students, I hope you understand today's class. If you really understand, please do like my videos, and remaining hybridizations we shall discuss in the coming classes. Thank you one and all for watching the Classroom Point videos.